Alright guys, last thing for today, I want to take you through a couple example problems and show you how to do these. So what we want to do is we're given a vector and we want to find the unit vector in the direction of v. So v is our vector. It travels 7 in the x direction, 4 in the y direction, so it's going to look something like this. There's v. Here are my axes. That's a little curved. So what we want to do is we want to find a unit vector that travels in the same direction as v. So what we need is something, unit vector means it has a magnitude of 1. Okay, so the magnitude of, and this is the notation, the unit vector in the same direction of v, we know is going to have a magnitude of 1. So we need something that, this is going to have a magnitude that's larger than 1. So we need something that's going to travel along that same path essentially, have that same direction as 7, 4, but only has a magnitude of 1. So what we're going to do is we need to figure out what the magnitude of v is first in order to shrink that down. So we want the magnitude of v. And in order to find that, we use Pythagorean theorem. We know we travel 4 in this direction, 7 in this direction. So we can find the magnitude using Pythagorean theorem. That's 4 squared plus 7 squared. Simplify that, you get the magnitude of v is equal to, that's 16 plus 49 is 65. So this will be square root of 65. That's the magnitude of v. But we want to write this thing as a unit vector in the same direction as v. So what we do is we're going to take this magnitude of v and we're actually going to multiply v by 1 over that magnitude in order to shrink that vector down, shrink that magnitude down. To get it to 1 where we want it. Okay? So the unit vector in the same direction as v. We know that the magnitude of v is 1 over root 65, or root 65. So we're going to multiply that vector v by 1 over the magnitude. And then take that vector v and write its components. So simplifying this, we've got the unit vector in the same direction as v. Again, we've got scalar multiplication here, so we just kind of quote unquote distribute that thing to each one of these components. And the unit vector in the same direction as v is going to look like this. Each one of those components of v multiplied by 1 over the magnitude. And we should probably rationalize this, so let's go ahead and do that. The unit vector in the same direction as v is going to look like this. 7 root 65 over 65, comma 4 times root 65 over 65. So you can check for yourself. This is kind of a nasty Pythagorean theorem to check, but this will have a magnitude, this unit vector will have a magnitude of 1. Alright guys, last example here. What we want to do is, this is really where it becomes useful to write things in that in the form of a linear combination of baseless vectors. Here we've got a vector v that has a magnitude of 30, so we know its length, and it's got a direction of 72. So if we just kind of plot this, there are my axes, and my vector is going to look something like this. 72-degree angle. It's going to go up somewhere around here. So I know that that's got an angle of 72. That's my alpha. And it's got a magnitude of 30. Alright, so what I want to do is I want to create this right triangle again. And what we want to do is we want to write this as a force vector. In general, a force vector looks like this. It looks like the force vector, and we'll label that F. and this is the force vector with respect to v. What we do is we're going to multiply this by the magnitude of that vector, and we want to multiply that magnitude by what we know about these different components. So we said the first component is the cosine of alpha times the basis vector I plus the sine of alpha times the basis vector j. So this is what your force vectors, this is the general form of your force vector. And again, it's useful if you know the direction of a particular vector and the magnitude. So let's go ahead and do this with this particular vector v. So we want to write it in terms of the force vector. We know the magnitude is 30. And cosine of alpha, well, alpha in this particular case is our reference angle. It's 72 degrees. So the cosine of 72 times the basis vector I plus the sine of 72 times that basis vector j. So we plug this into our calculator. The cosine of 72 is 0.309. I'm going to round that to 0.31. I plus the sine of 72, plug that into your calculator, and you get 0.95, about 0.951. So that's 0.95 times j. And again, that's multiplied by whatever your the magnitude of your vector is. So what we can do is we can write this as a force vector. We simplify, use that scalar multiplication. 30 times 0.31 is 9.3 times I plus 0.95 times 30 is 28.5. Times j. So this would be our force vector written in terms of a linear combination of our basis vectors. And again, we can switch forms, other forms, or that component form. We can write it as 9.3 comma 28.5 if we wanted to write it in that form. And just keeping an understanding of what this is saying. This is saying that this vector is going to travel 9.3 in the x direction, and in the y direction it's going to travel 28.5. And that makes sense that it travels more in the y direction than the x direction.